Today, we're going to continue working with the atomic structure and using the periodic table. So please make sure you have your periodic table out and a calculator. But we're going to be focusing on isotopes. I want to distinguish the difference between isotopes and allotropes. So allotropes is where you have different forms of an element, such as carbon, for instance. We know there are different types of carbon. We have carbon, the diamond. We have carbon in the form of graphite. We have carbon in the form of coal. Okay, so those are just three different types of carbon. Now, how those carbon atoms are arranged or put together is how you're going to get your different types or allotropes of your elements or your different types of carbon. Isotopes is going to be looking at the atomic structure of your elements. Okay, so we're going to be looking at your number of protons and your number of neutrons. So isotopes of your element are going to have the same number of protons or the same atomic number, but a different number of neutrons or a different mass. Excuse me. So, even though we say elements of the same element are exactly alike, they're really not. Their masses are going to be a little bit different. So, for instance, let's look at hydrogen. There are three isotopes of hydrogen. We have protium, deuterium, and tritium. And only one of those isotopes appears on the periodic table, not all three of them. First off, you don't have to worry about knowing how many isotopes each element has. I'll give you that information. So, hydrogen, its isotope that appears on the periodic table is going to be protium. And we're going to look at why in just a second. So, protium, its atomic structure consists of one proton, zero neutrons. So that means it has the atomic number of 1 because your atomic number and your proton number are the same. So if you could go on and also add like this little table to your notes, and its mass number is also 1 because your number of protons plus your number of neutrons will give you your mass. If we look at our second example, deuterium, it has one proton, which means it has the atomic number 1 also. To find its mass, it's 1 plus 1. It has the mass of 2. Tritium, it has one proton, so it also has the atomic number 1. And its mass is 3 because 1 plus 2 is 3. So as you can see, looking at an isotope, they have the same atomic number of 1, which means they all have one proton. That number never changes. Your atomic number or number of proton never changes under normal chemical reactions. If you're looking at nuclear reactions, that's a whole new ball of wax. Mass number is what's going to be different. So we have the mass of 1, 2, and 3 because your number of neutrons, they are different. We have 0, 1, and 2. Oh, the reason why protium, I forgot to mention this, the reason why protium is the one that's on the periodic table or the isotope that appears on the periodic table is because it matches up to the mass that's on the periodic table. So 1.008. Where they get that decimal point, because you can't have fractions or parts of protons and neutrons, is they do an average weighted mass. So that's where that decimal comes from. So if we would go on and round that 1.008, it rounds to 1. So that means protium is the most abundant, and it is the isotope that's on the periodic table. So it would be the one that you would come into contact more often or have a greater chance of coming into contact with. Isotope for carbon actually carbon has two different isotopes. We're going to look at carbon 12 and carbon 14. So our first isotope of carbon has 6 protons, 6 neutrons, so the mass is going to be 12. So if we look at the complete or nuclear symbol, we have the atomic mass or mass number in the upper left, the atomic number or your number of protons in the lower left. And this is what we call the hyphenated or abbreviated name. So you could say carbon dash or hyphen 12. So this is referring to the mass, or C-12, and it's red carbon 12 also. If we look at the second isotope of carbon, notice its mass is a little bit heavier. It has the mass of 14. It still has the same number of protons as 6, but notice your number of neutrons. It's different, it's 8. So your atomic numbers, they are exactly the same, but your mass numbers, they're different because 6 plus 8 gives you 14. So that's where your mass is going to vary for your second isotope. So this is carbon 14. Again, after the hyphen, that's going to give you the mass of your isotope. And carbon 12 is the isotope that appears on the periodic table, because if you look up the mass of carbon, it's 12.011. Again, the most abundant isotope appears on the periodic table. But what is carbon 14 used for? Carbon 14 is used for radioactive dating. Carbon 14 is actually found in the upper parts of our atmosphere. And all organic material is going to have parts of carbon 14 in it because we go through cellular respiration. Plants go through photosynthesis. So we're going to be absorbing some of that carbon in us. Carbon 14 has the half-life of 5,730 years. So what that means is after that amount of time, half of your substance will remain. So let's just say we had 10 grams of carbon 14. After 5,730 years, it has broken down and we have only 5 grams of it. So based on how much we have in an artifact that we find, how much carbon 14 is left in it, that is how we can date, knowing the half-life, the number of years it takes for your substance to break down and decay away. Now, some items, like say rocks, for instance, like if you're in a cave, your speleothems, your stalagmites and stalactites, those items are way too old to date. Okay, so you would have to use radioactive isotopes such as strontium and thorium, and that dating is way too expensive to do. So if you ever go on a cave tour and they're throwing exact numbers out, either they're using the natural history of what they know about the area of the cave over time to help date, or significant events that occurred around that cave during those time. But most of the time they're just guessing, because to be able to date speleothems in a cave, you have to take a core sample, and they're very fragile. They break very, very easily. And if you would try to take a core sample, it's just going to cause it to crumple and break, number one. Number two, like I said, it's just too expensive to date those items. It's too costly. So they'll just estimate or guess or just come up with their own numbers to make it sound interesting, depending upon what type of cave tour you're on. So let's practice. We have chlorine 37. Look at your periodic table and find chlorine, okay, Cl. And what is the mass that appears of chlorine on the periodic table? It's on the right-hand side of your periodic table. And I see 35.45. So the mass of chlorine 37 is not the mass that appears on the periodic table. So let's go on and add that to our notes slide.